Okay, let's start off with an example of current density. Let's say that we have a 14 gauge um, wire. Now, why 14 gauge? Gauge is a method to measure the diameter of wire, and it's been around for a long time. And if you're at all familiar with wiring of household electric systems, a lot of times wire will come in either 14 gauge or 12 gauge or 10 gauge, and it determines how big the diameter is. So the diameter of a 14 gauge wire is 51 mils. 51 mils is um, is 10 to the is 51 times 10 to the minus 3 inches. So um, it's given in units that are in English, so we'll have to do a unit conversion. But let's say we have this wire, and according to the safe code of uh, of of household currents, that 14 gauge wire should carry a maximum of 15 amps of current before a circuit breaker should trip or a fuse should melt. So let's figure out what does that correspond to in terms of what's the safe current density inside that wire. So we're going to assume this wire is cylindrical, as most wires are round. So we're going to assume that we have this cylindrical copper wire, and that it has a 14 gauge uh, diameter, which we have talked about is 51 times 10 to the minus 3 inches. So let's convert that into meters. So I'm going to pause the recording and do some quick conversion factors here. Okay, first of all, as I was looking at my conversion factors, I realized that I had read my gauge to diameter incorrectly. So it's not 51 mils, it's 64 mils for 14 gauge wire. So 64 mils is 64 times 10 to the minus 3 inches. You can kind of think of this as milli-inches. So I made a conversion factor to centimeters and converted centimeters into meters. So I get a diameter of my wire of 1.63 times 10 to the minus 3 meters. So of course the radius then of that would be half of that, or 8.128 times 10 to the minus fourth meters, or 0.81 millimeters in radius. Since I want to calculate current density, as my problem, I want to therefore use the definition of current density to be the current per cross-sectional area. So I'm going to take the current that I said was a safe maximum current of 15 amps and divide it by the cross-sectional area, pi r squared, and calculate our new current. So if you do that calculation, you get 7.23 times 10 to the 6th amps per square meter. So the current density is 7.23 million amps per square meter. And you may think, wow, that's a ridiculously large amount of current, but that's per square meter. So remember, that's a big cross section. So we're only using a very tiny fraction of that square meter in this particular example. Okay, let's do a problem where we are given a length of wire, and we want to find out how much power is being dissipated by that wire when it's attached to a particular battery. So let's say that we have a 9-volt battery, and we're going to connect it to 10 meters of 14 gauge, uh, and let's say we use there's a special kind of wire called nichrome. So we'll go ahead and use nichrome wire. Nichrome wire is an alloy of nickel and chromium and iron, and it actually has a pretty crappy conductivity. So it's actually got fairly large resistance compared to wires made out of things like copper and silver and gold and things like that. So you may wonder, why would you ever want to make a wire out of something that has really bad resistance? And and it's used in heating elements where you want it to dissipate a lot of electrical energy as heat. So if you look at those like glowing orange elements inside of a space heater or a electric stove or oven or something, they most likely are dealing with something made out of nichrome. So let's say we have 10 meters of 14 gauge nichrome wire and we connect it to a 9-volt battery. How much power is being dissipated by this circuit? So, well, we know that the power equation, power, is equal to I squared R for a resistive type element. So it'd be nice if we knew the current that was flowing through this thing. And here we could use the resistance of the object. Now, we don't actually know the current in this situation, so perhaps a better choice of equation for the power equation would be V squared over R. Were we given the voltage that's being applied to our circuit? Well, here's a diagram of our circuit. We're going to represent the resistance of the wire as an actual resistor, and here's my voltage. So the voltage change across the resistor is my entire 9 volts. So I do know both things in this equation. I know the voltage that's being applied to the resistor, and I would now need to know the resistance of that object. So let's go ahead and do that. Resistance, we don't know what, we weren't given the resistance, but we were given the shape and the material of the object, so we can use the resistivity relationship, rho L over A. So I need to know what the resistivity of nichrome is. So I would look that up somewhere, and in my case, I'm going to pause here and go find it. So at 1.1 times 10 to the minus 6 ohm meters, you can see that this material has a resistance, a resistivity that's about 100 times worse than copper. So now we need to get the length of it, which we were given as 10 meters, and we need the cross-sectional area, which again is going to be pi r squared for our object. Now, I picked 14 gauge because we have just done the problem where we did the cross-sectional area of a 14 gauge wire. So there it is there, pi times 8.1 times 10 to the minus 4th meters. So I'm going to go ahead and use that here in this portion of the problem. So I'm going to erase that r squared, put in my 8.1 times 10 to the minus 4th meters squared, and I should then be able to calculate my resistance. Now, what did I do wrong, or what did I do inaccurately here? Well, I used the temperature, the resistivity at room temperature, and if we're letting this thing heat up, this wire heat up, that resistivity is not going to be accurate anymore. But since this is just an example problem, I'm going to let that go. And so let me do this calculation and we'll see what we get. So our resistance here is 5.34 ohms if we do our calculation right. And so now I should be able to figure out how much power is being dissipated by my circuit. So the power is going to equal V squared, which we know is 9 volts squared, all over the resistance, 5.34 ohms. And I can do that now real quick too. So that comes out to be 15.2, and now we need some units. And so we could quote this as volts squared per ohm, but we are all familiar with a unit, the proper unit of power, and that works out to watts. So this would dissipate 15.2 watts worth of power here. Now the question is, how long can a 9-volt battery produce 15.2 watts? Probably not that long. So this is why you don't run heaters and other things like hair dryers off of battery power. So fairly large heat there. But how's that compared to, say, for example, the power requirements of a hair dryer? How warm are you going to get, or how dry is your hair going to get with a 15.2 watt heater? And the answer is not very. A typical hair dryer might have, say, a 1500 watt or a 1200 watt hair dryer. So if our power is 1500 watts, let's figure out assuming that we have standard wall current. We plug this into the wall. We turn it on. You notice how sometimes in your house your lights dim a little bit briefly while you turn on the hairdryer. Let's assume that we're running that at 120 volts. Uh, so our voltage is 120 volts. Whoops. So given that, how much current is being used in my circuit by my hairdryer when I'm running it? So how much current's being used? I. Well, we have to find a relationship that's going to relate power with voltage and current. And we know the standard definition of the power in a circuit is going to equal IV. So if I rearrange that equation to solve for I get I is equal to P over V. And so with my 1500 watt hair dryer, and I am going to power that with a 120 volt electric circuit, I would get an answer of a little over 10 here, 12.5 amps. Now, if this is in a household, and we just learned that a lot of houses have circuits with a maximum of 15 amps allowed in a circuit, you plug in your hairdryer in the bathroom, and if it's on the same circuit as the lights, which are drawing a couple of amps themselves, you can see how quickly you could get to the 15 amp limit. So if you have a lot of lights on the circuit and you turn on your hairdryer and suddenly all the lights go out, it's because you've now gone over the 15 amp limit on your circuit. So these have been examples of the basic calculations you would be making with the definition of current, current density, resistivity, how the resistance is calculated from the resistivity, and power in electric circuits. Next chapter will be about how you can combine more complicated circuits together that have multiple elements, multiple loops, and still use these fundamental concepts, but arrive at solutions for much more complicated circuits.